This conference will now be recorded.
Hello, everyone. This is session 6, our last session of the machine learning short course from CIRA. And what actually happened was that at the actual lecture, I forgot to hit the recording button until about 50 minutes in. So Ryan and I are now just re-recording the first part of the lecture without any attendance, just so that we have a complete set of all of the presentations. So with that, let's get started. So let me share my screen. All right. So again, this is the last session of our 6 lecture class. And we're going to discuss today a bunch of things that I think are important for you to go out in the world and use machine learning on your own. So this session first covers some general guidelines and recommended reading. And again, this is to give you additional material to go beyond what we covered in the class. And we put it on in the beginning on purpose because we wanted to make sure we have enough time to cover this. After that, we're going to go into image-to-image translation networks, such as encoder-decoder networks and Unets. And in order to understand those, we still have to discuss upsampling layers, so that comes first. But once you know these image-to-image translation tools, you will have all the tools to understand the CIRA applications in more depth. So we will cover 3 different applications at that point. And then finally, we will go into generative adversarial networks, also known as games, and then we will wrap up. All right, starting first with some general guidelines. So if you think of machine learning, clearly that's been developed for computer science. And the use of machine learning for computer science is a little bit different, though, than for meteorology. In particular, there are significant differences between how you use machine learning for classic computer science applications versus machine learning for meteorological applications, to a large part because we have different types of data and tasks. So what we try to teach in this course is machine learning for meteorological applications. All of the notebooks that Ryan prepared for you that came with this course really show you how to use machine learning specifically for meteorological applications. However, sooner or later, you will have to adopt methods directly from computer science, either because you want to do things that we didn't teach you in this course, or simply because you want to explore new methods and there simply aren't many resources yet for meteorology. So what we do in the next few slides are 2 different things. First, we go through some recommended reading and resources that come from computer science. And then we show you some guidelines on what to be careful about when transferring the methods from computer science to meteorology. There are certain things you want to take over, and there are certain things that you do not want to take over. All right, starting with recommended reading. And again, these resources that we're showing you on this page all are from computer science. So you have to be a little careful with them, as we'll show in the later slides. So first, some resources for general machine learning. My favorite book by far is by Aurélien Perron, and it's called Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow. So this is a highly recommended book that really includes everything from clustering, decision trees, and neural networks. It's excellent for beginners. It has lots of examples that you can try out right away. It also comes with notebooks. It's also good for people who already know machine learning a little because it really gives great motivations as to why certain things were developed the way they are. So highly recommended book, especially if you're starting out on machine learning. There's also online documentation and tutorials for scikit-learn, because basically what you're going to use when you use general machine learning, if you don't use neural networks, you're likely to use Python and scikit-learn. And so it makes sense to go to the official scikit-learn website, and they have a very detailed user guide with code examples for all different functionalities and notebooks and everything. So I highly recommend going to the scikit-learn website if you use scikit-learn for clustering or decision trees, etc. The next set of resources is specifically for neural networks. If you use neural networks, you're likely to use Python and TensorFlow with Keras. So TensorFlow and Keras go together. PyTorch is another very common tool. In fact, TensorFlow was developed by Google and PyTorch was developed by Facebook. And they're both fairly common. You might find PyTorch more in computer science department, especially when you do a little bit more theoretical research. However, both CIRA and especially NOAA mainly use TensorFlow. So since you're CIRA and NOAA people, you're likely to use Python and TensorFlow with Keras. Because of that, we mainly list the main resource here being the official TensorFlow and Keras website, which you can find at tensorflow.org. And I will actually show you that web page in a second. There's a very classic book to go deeper into TensorFlow. So that's the book by Ian Goodfellow and Benjio and Covell. Goodfellow, you may know, is the inventor of GANs, and Benjio was one of the inventors of deep learning. So this is a great book, and maybe Ryan, do you want to say more about this book? It's one of your favorites.
Yeah, the deep learning book I find is a good resource for someone who already knows a fair amount of machine learning but just doesn't know a lot about deep learning, because at least that's the way I approached it. But looking here again at the chapter list, there's 3 parts of the book. So part 3 is deep learning research, part 2 is modern practical deep networks. So 2 of the 3 parts are devoted to deep learning, but part 1 is actually applied math and machine learning basics. So it teaches you about linear algebra, probability and information theory, numerical computation, and then machine learning basics. So it also gives you a crash course in the theory of machine learning before jumping into deep learning. And I just find I've cited the Goodfellow book in a lot of my papers and also my dissertation, because I find that there's some really basic concepts in machine learning that are sort of common knowledge in the field of machine learning, but not in atmospheric science, who are mostly the people reading my papers. So when I need a citation for a concept that's common knowledge, I often go to the Goodfellow book because it's one of the few places I can actually find something explained.
All right, thank you. And then the last resource we're listing here are the Jupyter notebooks that come along with the Deep Learning with Python book. And we actually really like to use the notebooks, even if you don't have the book. The notebooks are great. You can use them without the book. And here's the link for those. Now, I wanted to just jump briefly more into the TensorFlow Keras online resources. So you can find the TensorFlow tutorials at the webpage given over here. And what you find is a collection of notebooks with explanations. It includes a quick start guide for beginners and also a library of models. And it's just a great starting point for learning how to code simple models in TensorFlow. So let me show you briefly. Let me just show you. If we go to the tensorflow.org website over here. Oops. So if we go to the tensorflow.org website, this is what you see. And it shows here at the top, there's resources for TensorFlow and other things. We would definitely want TensorFlow. So you can just click on Get Started with TensorFlow. And then takes you to a website that has 2 different main menus. One is tutorials and one is a guide. And feel free to explore both, but we will go to tutorials for a moment. And what's really important is on the left-hand side, you see now this menu. And so if you, for example, want to look for neural networks that work with images, such as convolutional neural networks, you will want to go on images. And if you click on this, you will see here convolutional neural networks. So you can click on those. And then you may just want to go straight and click on Run in Google Colab. Here we go. And so this will give you an absolute minimal example for a small convolutional neural network and how to code it in TensorFlow. And the first thing you will notice is just the very, very few lines of code. So it's just the usual introduction here where you load the modules that you need. Then this one is a very simplified version of reading in data, which is already pre-prepared for you. So it's just one line. And keep in mind, usually when you prepare data, it's like 90% of your work is just getting the data into the right shape. So, and properly pre-processed, so that they only have one line here may be a little misleading. And then there's a little bit more preparation, and then it already goes into the model. So here's the TensorFlow model is defined as a convolutional network. It just says we want a sequential model. First, add a convolutional layer, then add a max pooling layer, another convolution, another max pooling, another convolution. With that, those 5 layers are already defined, where you define what your activation function is, etc. And then you can add dense layers on top if you want to use this convolutional network for a classification task. You do that here by flattening, adding 2 dense layers, and you can print the model summary. This one shows you how to then compile the model, and then this is where you actually train it. And then you can plot results. As you can see, an absolutely minimal model of the convolutional neural network. Okay, so going back to our presentation. The whole point is I wanted to show you that you can find these resources there. If you want to implement a game, you go follow the same way and then go to generative models and pick whatever type of game you want, maybe pix-to-pix, etc. So I just want you to be fully aware that this is always a place where you can go look for different minimal instructions for doing a certain type of neural network. Now we just want to spend a minute to talk about what to carry over and what to replace. So the way I see it, I always call it a psychological trap. Because since the newest neural network techniques come from computer science, they're usually illustrated for computer science applications and they have very different properties. And so when you transfer these techniques over, it's very tempting to carry over everything because it's one block of code and that includes the performance measures. But those performance measures usually don't work well for methodological applications. So briefly on this side, what you should adopt with minor modifications are the general machine learning models and the implementations. For example, neural network models that perform certain tasks such as classification, image-to-image translation, etc. You can even go one step further and not only move over the architecture, but do something that's called transfer learning, because sometimes it's even useful to adopt a trained neural network model, which already has all of the weights and biases trained, and then fine-tune them for methodological applications. Again, this is called transfer learning. And transfer learning just means you transfer something that's been learned in one task to another task. Why would you do that? Well, there are tons of models trained, for example, on the ImageNet dataset, which has 40 million images and each is labeled with 20,000 different object labels. And every year there are more and more networks available that work really well for ImageNet classification, and they're publicly available and often used as a starting point, for example, for land use classification from satellite imagery. And the reason to use them is that we usually don't have enough labeled data in methodology. So if you can take a network that has already learned a lot about low-level features and images and how to analyze those, you can take that over and just retrain the final layers in the hierarchy to adjust them to your model, and you might get much better results than if you train a neural network from scratch. Also, you may want to consider that you should generally use as much of your expert knowledge about applications as possible for model selection and design, and we'll have a slide on that later. Things that you should not carry over, so you should either replace them or at least examine them very critically, are two primary things. Number one, how to split data into training, validation, and test sets. We talked about that in detail in lecture 2, so just go to lecture 2 for guidelines, but I just want to remind you that our data typically has spatial and temporal autocorrelation, which is usually not the case in computer science applications, or not in the primary ones. In computer science applications, you often have different users that send in different requests on web pages, so each entry in your samples, each sample basically is usually independent from the other samples by itself. And that isn't the case for us. So we have to work much harder to create independent training, validation, and test sets. So just go back to lecture number 2 for guidelines and keep that please in mind. The other thing that's important to look at are loss functions and performance metrics. For example, accuracy is a very common measure in computer science, but just not meaningful as measure for applications with rare events. And we get to that in a second again. So methodologists have carefully designed really meaningful performance measures for decades, and we should use them as much as possible. We can always use them for evaluation, and many can even be implemented as a custom loss function. However, for loss functions have to be differentiable, and it's a little tricky to implement them. And we're here at CIRA in the process of creating some resources for that, because I think that the methodological community could really benefit from having resources on custom loss functions. Again, see lecture 2 for some examples of performance metrics. Ryan covered them in great depth. But basically, always try to use metrics used traditionally for methodological applications, also when you use machine learning algorithms. With that, just a quick example on how silly it might be to use accuracy as a measure for rare events. If I ask you, is it Halloween today? And you give me a model that always says no, your answer is going to be correct 364 out of 365 days, which means you have an accuracy of over 99.7%. But if you want to use a similar model to predict tornadoes and you just always say no, I don't think people would be very happy with this model. So the key point is your accuracy can be way over 99%. That doesn't mean you have a good model, which just shows again that you really have to use measures that are meaningful to meteorologists. So don't forget that. Other recommendations, you should always compare your model's performance to meaningful baselines. Sample baselines can be climatology. It could be persistence forecast. Say you want to predict what the weather's like tomorrow. You could just take today's weather and say, I'm predicting that the weather tomorrow will be the same as it was today. And then you have to show that your neural network or whatever you're using actually works better than this. Also, you may want to use very simple interpretable methods such as linear regression. First, show how much better your method is in comparison to linear regression. And if it's not better, then use linear regression instead. And also compare to whatever method is currently being used. Secondly, always pick the simplest machine learning method that does the job. Start with a simple model, and if it works well, stick with it. Use higher complexity algorithms only if they make a real difference in precision. So we often start with a real hierarchy of models. We start with linear regression and we go further and further up. And once the more complex models don't give us more precision or anything like that, we just stick with the simpler models, because there's generally a trade-off between precision and interpretability. The simpler models are much easier to interpret, and the more complex model may give you more precision, but if that's diminishing returns at some point, you're better off using the simpler models. So you should ask yourself, what is more important in your application? Is precision more important or interpretability? Will your algorithm even ever become operational if it's not transparent? If it's too black boxy, it might not be used even if it gives great results. And should you give up some precision to get a simpler algorithm that is easier to understand? Likewise, ask yourself, as we mentioned before, whether you can use your expert knowledge to design the architecture. You may start out by just wondering, how would a human solve the task? How would existing algorithms solve the task? And that will be a great guideline for choosing the variables accordingly that you use as inputs, and can also help you to give the machine learning algorithm maybe a similar structure. Maybe the overall task can even be broken into smaller modular tasks, and some of them can be solved with machine learning, and others maybe are solved with traditional methods. And if you can do that, maybe you just go with machine learning for the last mile, and that increases interpretability. Lastly, when you're trying to figure out what architecture or method to use, look at problems of similar nature in literature or in the community. What methods have been used for those? So again, you can start with an architecture method that is used for similar applications and just see whether that works for your applications as well. That's usually a good starting point. And as we mentioned before, you can even take a trained network from another application, fine-tune it for a new one. That's called transfer learning. Ryan, do you have anything to add to this?
I think partly reiterating what you said, I often find that a good starting point for my projects is looking in the field of atmospheric science and seeing if someone has solved a similar problem with machine learning. So, for example, if I'm trying to use machine learning to predict damaging straight line wind, and I see that someone else has used machine learning to predict tornadoes, and we're both using storm-centered radar images, or to be even more general, we're both using image data. I may go look at what the other person did, and I may see, oh, they used a convolutional neural net with 3 layers. So that may be my starting point. I'll say if it took that much complexity for their model to work, they needed a CNN with 3 layers. I may start off with a CNN with 3 layers, and that will be sort of the initial seed, and then I'll tweak my model complexity around that. So when I do my hyperparameter experiment, I'll try CNNs with 4 layers and 5 layers and 6 layers, and maybe I'll try a CNN with 2 layers, and maybe I'll try a fully connected neural net as well instead of a CNN. But that'll be sort of the CNN with 3 layers will be sort of the average, quote unquote, of all the models that I attempt, because I know that it worked well for someone in the past solving a really similar problem. So if someone else in atmospheric science or whatever your application domain is has used machine learning before to solve a similar problem, I find that's always a good starting point because they've dealt with similar issues that you have. as opposed to taking a model from computer science where the data and the evaluation methods, et cetera, are just generally so different.
All right, thank you. And at this point, we often get the question of how do you find out what else has been done? Because not everybody has the time to read everything that's coming out constantly. And for that point, conferences are really helpful, but also building a community, talking to other people who are in your application area and just exchanging regularly what kind of papers you found. For example, I'm on several Slack channels where whenever people find interesting papers, they post them there, and then you can look at whether that's interesting. But we also have weekly discussion groups where we just discuss what kind of new things have come out or what's interesting, or give each other an introduction to a quick topic. So the key point is working with others is really important, and that's part of what we're trying to do here, is to build a community of people who can talk about similar topics. And as we discussed before offline, we're thinking about offering either every second week or once a month a little meetup of people from this group to just talk about topics like this, but we'll get to that more later. All right.
I think
and
to
this
reiterate what you said, sorry,
yes.
to reiterate what you said about conferences, I found that really useful, especially in the last couple of years, for tracking the explosion of deep learning and atmospheric science. Because deep learning as a field itself is so new, but then deep learning applications in atmospheric science are even newer. So a lot of this stuff hasn't made it to publications yet. So if you want to find out like what the cutting edge of the field is right now, I find that a really good place to start is look at the AMS artificial intelligence conferences. And if you really want to see how much deep learning is being adopted in the field, for example, as just one example out of several methods, if you look at the abstracts from AMS 2020 and AMS 2021, you can really see how incredibly popular deep learning has become. Whereas if you look at the publications, those are obviously lagging behind. So you'll find maybe a couple dozen publications, but probably over 100 abstracts on deep learning within just the last 2 years. So I find that's always a good place to go if you want to figure out what the cutting edge is and where people are going.
Great. And I fully agree. Looking at the abstracts is just a quick way to really figure out what's going on, kind of getting a pulse on what the newest developments are, and then deciding which talks you want to attend, especially since this year they're going to be recorded, a lot of them. All right, this is just a slide from lesson 1 that shows you again the trade-offs for the different methods. And the key point again is keep in mind, really don't necessarily start up here. Start somewhere down here and work your way up. And always keep in mind that you're paying a price, that if you go to deep learning, you might get higher accuracy and you can model nonlinear and more complex patterns, but you're also losing interpretability. So don't neglect other things. Random forest works great for many applications. And if your problem isn't very nonlinear, even linear regression may work well. So just consider this trade-off between simplicity and potential precision. All right, with that, moving on to our next topic, image-to-image translation. So image-to-image translation networks are usually CNNs that transform an image into another image. In order to cover those, we first need to introduce one more layer type, the upsampling layer, and then we can discuss typical CNN architectures. And we will cover today the encoder and decoder networks in Unets and later then GANs. And so let's start just with a quick recall of what Ryan explained last time about pooling layers. So I just wanted to remind you, because upsampling layers are kind of the opposite of pooling layers. So a pooling layer, again, is used to reduce the resolution of an image by combining groups of pixels. So in the example down here, you see a max pooling operation applied with a 2x2 filter, or with a stride size of 2. So what happens is basically you take a 2x2 non-overlapping area over here, and you take, for example, the red area, you take the maximum number, and that becomes a 6. You look at this green area, the maximum is an 8, you put the 8 over here, so you get an image that has half the resolution, but just maximizing the different areas here. All right. If you're trying to do upsampling, you're really trying to reverse the pooling. So you're trying to go from the low resolution image you just generated to something of higher resolution again. Of course, that isn't really possible because you lost a lot of information. We'll get to that in a second. But first, I just want to let you know that there are two standard methods in CIRA that you can use for the interpolation. You can either use nearest neighbor interpolation, which is the default, or you can use bilinear interpolation. There are a bunch of other methods you can use too. So what would you get if you use the default, the nearest neighbor interpolation with a 2x2 mask and a stride of 2? You would basically just copy over value into 2x2 blocks. So you take your red 6 over here and you convert it to a block that now has 4 numbers, but they're all identical 6. Same thing for the 8, same thing for the 3, same thing for the 4. So really, you haven't added any information. You just restored the dimensions of the image, and in a way the resolution, but in terms of information, this still doesn't have any more information than this. And if you choose bilinear interpolation, for example, that yields a slightly better interpolation, but it doesn't do a whole lot for you either. So what do we do instead? We keep in mind that upsampling only restores the dimension from before pooling, but not the information. Again, different interpolation techniques can be used, but the most common ones are the nearest neighbor, which is as simplistic as this, or bilinear interpolation. But what you do instead of having something very fancy there is that you add a convolution layer immediately after the upsampling layer, which will then try to learn more complex patterns to fill in the information. So just keep in mind, the purpose of the upsampling layer is really to give you something that has the right dimensions again, and that keeps the very basic information, but you always add convolution layers to help you actually fill in the remaining information with better interpolation. Okay, with that, you now know what upsampling layers are, so we can now explain to you the image-to-image sensation architectures. And just here, putting it all together, I'm showing you here diagrams where each layer is indicated as a block denoting its function. And you will see in a second, there are two different types of diagrams. So this actually threw me at the beginning. I was very confused at first when I was looking at different papers, because they're really two different ways of representing neural network blocks. You can represent the functionality as we do here, or we can show the input and output as we do in the next slide. So here, each block, this, for example, with the C is a convolution layer, 3 by 3, another convolution, pooling, convolution, convolution, pooling, convolution, convolution, pooling. So what this does, this is the type of network that was discussed last week that is for image classification. So this first block extracts patterns from the input images. So what comes out of here is a very abstract description of what kind of contextual patterns the neural network found. And then the last 3 layers are, which are these, which stands for dense or fully connected layers, are there to interpret which patterns were found to then assign an output label. So in the classic image classification task, you will always have a combination of convolution and pooling layers early on, but then followed by dense, or also known as fully connected layers afterwards. In contrast, the image-to-image translation networks do not have dense layers, because the output in that case is an image. You're going from an image to an image, so you're not using fully connected layers ever. What you use instead is that you have this first block, which in this case has convolution, pooling, convolution, pooling, convolution, pooling, but you could have just as well taken the one up here. They're very similar. That extracts again patterns, which in this so-called bottleneck layer, which has the lowest resolution, then represents the patterns you found up to then. And then you have this expanding layer, which is kind of the opposite functionality of this one, to expand your bottleneck representation to again come to an output image. Let me show that to you in a different kind of diagram. So here you see that each layer in this diagram is indicated by the image size. So this is a very similar network to the one I showed you before for image-to-image translation. The input is an image, the output is an image, in this case is segmentation. And you really go, the blue things here are convolution, and you see convolution, the image size is about the same. Then you apply a pooling layer, and then the image size drops. Then you have convolution, you have pooling, the image size drops again. So this representation is better for showing you kind of the size of the images that you get. And here in the middle is a bottleneck layer I mentioned before, and then you expand again. And one way to think of that is, I like to compare this to language translation. So say you have a sentence that's given in one language on the input and you want to translate into a different language at the output. as you all know, you can't translate a sentence word by word. It's not going to give you good results. You need the space, you need the context of the surrounding words. Just like in an image, you can't interpret pixel by pixel. You're much better off taking the context of that pixel into account to understand what that pixel means in that context. And so the way to look at that is that here, by using those pooling layers, you're basically extending your context. You're taking more words into account, so you're taking more pixels into account to understand the meaning. And here in the middle, you have the most abstract representation where you now present, you basically have a representation of what these words mean or what this group of pixel means. And once you have this abstract understanding of what your words mean in that sentence, you can then start to translate it over into your different language or into your different image space and expand it in that representation. All right. So again, here you have your original representation and you have your different representation. And of course, we wouldn't feed in an RGB image, we might feed in several different ghost channels. And then at output, you can either get a meteorological segmentation map that asks the question, does a pixel belong to a tropical cyclone or not, or does it belong to a convective cloud or not? Or you might create a synthetic image. So you might feed in ghost imagery over here, and out comes Mrms imagery. So that's just like translating from one language to another language, say from English to German. You might have instead going from ghost imagery to Mrms imagery. All right. So one last trick before we go into the applications. Basically, we showed you the encoder-decoder architectures that go down and go up again. And there's one more trick to get you to a Unet. Because as we know, yes, we can add the convolution layers after the upsampling, which here now is called unpooling. But it's the same thing as what we called upsampling. It's just a different word for it. But you really, it's really hard to really restore the resolution fully if you don't have any of the previous high resolution images fed in. And so the idea of skip layers is to just skip some of those layers and go directly with information from here to here and feed that in additionally. So you have the same pathway as before, your encoder-decoder network, which is just these things over here. So you go down, you go up again from layer to layer, but in addition, for example, this layer, you get the information from the previous layer, but in addition, you also get the information that was in the other space at the same resolution. So that additional information helps you to now interpret what you're getting here in the context you've already learned through this pathway. But it really helps you to expand and get higher resolution results. So with that, you now know what a Unet is, but you usually see it more in this kind of representation. And that also explains why this is called a Unet, because this is now, this pathway here is the same pathway we had straight before, but now we draw it as a U. So this is convolution, convolution pooling, convolution, convolution pooling, etc. You draw it in this way because now you can draw the skip layers as just horizontal connections. And this U shape of drawing it again is the reason why you give this a name Unet. With that, you now have all the convolution network tools to understand more applications. And with that, we'll briefly go into applications. 3 different ones. The first one I discussed, going from ghost to synthetic Mrms imagery. Then we will look at forecast and convection from satellites and radiative transfer, which will both be covered by Ryan. All right. Starting with going from ghost imagery to Mrms or radar imagery. So this was work done by Kyle Hilbrand and myself, where we try to generate synthetic radar imagery from ghost channels. And obviously we're using convolutional neural networks. In fact, we use an encoder-decoder architecture, just like you saw before. So the idea here is you want to go from your input images, which in this case are 4 ghost channels for each sample, to the output image being Mrms radar estimates. So here you just see one sample. So here's 3 different input channels, including the GLM lightning channel from ghost. And this would be what's given to the neural network. And then you train the neural network to then spit out something that's as close as possible to the observed image, here the Mrms. So this is our estimate for this. And that's a little bit more blurry, but at least it's a lot better than the original ghost imagery. So it does a decent job. It's not perfect, but it does a decent job. And so the idea again, of course, is that ghost imagery is available in all of the continental United States, but Mrms is not. So we're thinking it would be helpful still for forecasters to have something like this. And we're still working on making it less blurry. But in any case, so we got a neural network that has this architecture. And that's really very much like what you saw before. It's a standard encoder-decoder network. We also tried Unets, but they actually didn't do much better in our case. So we just stuck with the encoder-decoder layers, because then we could use visualization techniques that are not available for Unets yet. So again, you have your encoder layer, your decoder layer, you have as input your ghost channels, as output your Mrms estimate. And this model we called Gremlin for Ghost Radar Estimation via Machine Learning to inform NWP. And I have to admit that we chose the name of it in order to give us this acronym, Gremlin, which Steve Miller came up with, and we just really liked. So Gremlin works reasonably well, but we were wondering, how does it do it? And there's 3 different interpretation methods that are in the next 3 slides, and we will go through them only very quickly, but just to give you an idea of how we analyze this model. So the first one is called an ablation study, and you can take all your time to study this on your own. I will just tell you briefly the whole idea of an ablation study is that you basically come up with a hierarchy of different neural networks that have smaller capabilities than the final model. So what you see here at the top is your ghost input channel, and then what is produced as output for a neural network that was trained on just a single input channel, channel 13. And then what you see at the bottom is a hierarchy of 1, 2, 3, 4 different models, where sometimes we don't give the neural network our ability to interpret spatial patterns, but only go pixel by pixel, or we give it more than one channel, etc., etc. So again, it's a hierarchy of 4 different models. And what you can basically see is that the final model, Gremlin, does really well. But even one that's a little simpler, that only uses 1 channel instead of 4, does pretty well too. But if you take away the ability for the neural network to see spatial context, you get really bad results that don't match your desired output at all. Another side that I won't go too much into is the use of layer-wise relevance propagation. And the key point here is you can use layer-wise relevance propagation to ask the neural network where it was looking when it came up with this prediction. So in this case, since we're predicting certain output values, we were wondering where in our input channel was the neural network actually looking, and LRP can tell us that. So we saw, oh, in order to predict a high Mrms value, the neural network is either looking for cloud boundaries, which are large gradients here, or is looking for high brightness, or is looking for the presence of lightning. And those were the key triggers. This one we'll discuss in a little bit more detail. So this was an idea that Kyle Hilburn had to actually feed synthetic inputs into our trained neural network. So here he designed synthetic inputs using generalized elliptical Gaussians. And in this animation here, you can see simply how the impact of at which angle your feature is. This is again, you're feeding this instead of the ghost channel, in this case, channel 13, into your neural network. Just the angle, how that changes the output. So as you can see, the neural network really responds differently depending on the angle. So clearly has learned something about the wind direction in the data that we gave it. And the key point for using those kind of synthetic inputs is that you can then do very controlled experiments of how your neural network is behaving. You can feed in inputs for specific meteorological conditions and see how the neural network responds without having to worry about anything else that's in the image. And you can also find the inputs that generate minimal or maximal response. And then I wanted to just show you the typical workflow for neural network interpretation methods, and especially make the point that this is really driven by meteorologists, not by machine learning scientists. So if you try to interpret neural networks that were developed for meteorological models, really your neural network interpretation is the process of hypothesis generation and testing. And in fact, the neural network interpretation tools are just useful tools in that process, but they don't drive the process. The environmental scientist or meteorologist is actually the one who's driving the whole process, as I will explain to you in a second. So let's say you're looking at, you want to analyze your neural network and you want to figure out how it works for different kinds of meteorological conditions. So you will probably select a set of samples, and here just some examples of how you can choose a set of samples. But this is again really driven by the methodologist. So we're now in step 1 of the simple sample analysis step. So the methodologist selects a set of input samples to focus on. And Ryan will give you examples of that in his applications in a second. So once you've selected your set of input samples, maybe everything that created a strong hailstorm or anything that happened at a certain hour of the day. So once you've selected this, you run the set of samples for your neural network. And then for those samples, you look at the corresponding output of the neural network, but you also look at results from neural network visualization tools, such as the layer-wise relevance propagation that I just showed you in the previous slide, which can tell you where the neural network was looking, where it was paying the most attention on the input in order to come up with this output. And then you also should look at performance measures for the entire set of selected input samples and for outliers. Then it comes back again to the methodologist, who will now interpret the results from step 3. And based on the observations in step 4, the methodologist is likely to generate more hypotheses of what neural network strategy thinks the neural network is using. And if needed, then we then design a follow-up experiment to test the hypothesis. So it may say, well, I think if a storm is like that, then the neural network will spit out a certain output. And so then the methodologist would say, okay, let's look at certain samples that have certain properties and just run through the whole thing again. So it's really an iterative process. There's no automatic tool where you feed your neural network and out comes an explanation from methodologists of how your neural network works. This is really a close collaboration of the methodologist and the machine learning scientist to really go through this loop many times until you think you have a good understanding of what the neural network is doing, why it is making the decisions it is making. So for everything I showed you in the previous slides, if you want to have more details, it's all explained in this paper, so feel free to look that up. With that, I will turn it over to Ryan.
All right, so this is the second of the 3 CIRA applications, and this is something that I've been working on in my postdoc for the last few months, and it's forecasting convection from satellite data. So the whole motivation for this is that short-term forecasting of convection, as in over the next few hours, is really important for many applications, including outdoor events and aviation. So for example, if you can be confident that convection will initiate near an airport within the next couple hours, maybe you need to reroute some planes and decrease the number of planes taking off, decrease the number of planes landing at that airport, etc. You may need to delay or cancel an outdoor event. And in Taiwan, it's also really important for flash flooding because of the topography they have and also just the prodigious rainfall rates they get out of convective storms. So the motivation for doing this from satellite data using satellite as predictors is that where radar coverage is sufficient, radar is the best way to determine where convection is happening now. So if you want over a large domain the best possible estimate of where convection is currently, you look at a radar map, you look at a map of composite reflectivity or echotops, for example, and that's the best way to determine where convection is happening at the present time. But radar coverage is not sufficient over most of the globe. So most countries don't have a great radar network. Even Canada, where I come from, way less than half the country is sufficiently covered by radar. And even in countries that have a good radar network, there's all kinds of issues with coverage where you have complex topography. Taiwan is no exception because they have a really large mountain chain running through the middle of the country. So there's lots of places in Taiwan where even though they have a good radar network, the radar coverage isn't great. Whereas, so as opposed to radar, which only covers certain parts of the globe, satellite basically covers the entire globe. And they have a fairly new satellite called the Himawari 8 that provides really high resolution data covering all of Taiwan. So the motivation here was to use the Himawari 8, use all the satellite channels, so all the spectral bands that the Himawari 8 measures as predictors for where convection is going to occur at different lead times into the future. So for example, we could use the Himawari 8 satellite data to estimate where convection is happening now, but we could also use a time series of the Himawari 8 satellite data. So for example, if we need to issue a forecast right now and we want to know where convection is going to be in the next hour, we would look at the satellite map now, but we would probably look at the satellite map at a few time steps in the past too to get a history. So we could look at the Himawari 8 satellite scan right now, and then we could take 10-minute time steps going back 1 hour. So we could look at a whole bunch of different time steps from the satellite data, and then the job of the machine learning would be to extrapolate forward 1 hour or 2 hours or whatever the lead time may be and figure out where convection is going to occur at the target time. And another motivation for doing this is that high resolution satellite data has only been available for the last few years, so we feel that it's really underexploited. We think there's a lot of things that can be done by applying machine learning to this new high resolution satellite data, and these things just haven't been done yet because the high resolution data is so novel. So we finally have enough of it that we can start training really big machine learning algorithms.
All right, and if you want to hear the rest of this presentation, we will now stop this recording because now we can go over to the part that was actually recorded.
This conference will now be recorded.
Oh, I see the recording was just turned on.
Yeah, I forgot to record, so I'm just recording for now. Never mind, sorry.
Sure. So most countries, including where I come from, Canada, don't have a very good radar network. And even in countries that have a better radar network, there's because of topography, there's a lot of areas that aren't very well covered by the radar network anyways. So radar only covers a small portion of the globe sufficiently, whereas satellite covers the entire globe. And also high resolution satellite data, which is available only for the last few years from the new GOES constellation and the Himawari 8, for example, is underexploited. We think there's a lot of things that can be done with machine learning to exploit this new high resolution satellite data, and these things just haven't been done yet because these data sets are new. So I'm going to show you some examples of the predictors and then the targets for my Unet. So this, I know this 9-panel figure is a lot, so I'll walk you through it. So the top 2 rows and then the bottom left are showing you brightness temperatures for 7 different spectral bands from the Himawari 8 satellite. So if you look at the top row, the middle row, and then the bottom left, these are all basically the same map, just for different spectral bands. And I don't remember the wavelengths that these bands correspond to. They just have integer numbers to label the bands. So the bands are 8, 9, 10, 11, 13, 14, and 16. The color scheme in all 7 of these figures is the same. So it goes from 190 to 310 kelvins. Lower brightness temperatures mean higher brightness and higher cloud tops. So generally convection corresponds to areas with lower brightness temperatures. So those purples and yellows. So that's what you're seeing in those 7 panels there. And then in the bottom center panel, you're seeing the composite reflectivity, or they call them maximum reflectivity, at every single grid cell. And you'll notice that there's, if you look at the titles in the panels, there's a bit of a temporal offset. So the satellite maps I'm showing are valid at 0110 Zulu or 0110 UTC, whereas the composite reflectivity map is valid at 02 Zulu. So this is a neural net that I'm training to forecast where convection is going to be 30 minutes into the future. So the forecast time, or the initialization time, is 0130 Zulu, and I'm using predictors from 3 different lag times. So I'm using the satellite brightness temperature maps now at 0130 Zulu, but also at a lag time of 10 minutes and a lag time of 20 minutes. So at 0120 Zulu and 0110 Zulu. So if I flip through the next 2 slides, the only thing that changes in this paneled figure is the satellite maps, whereas the composite reflectivity and the bottom right panel, which I haven't really told you about yet, those stay the same. So only the predictors are changing as you go through these slides. So on this first slide, you're seeing the predictors at 0110 Zulu, so a 20-minute lag time. Here you're seeing them at 0120 Zulu, so a 10-minute lag time. And here you're seeing the predictors at 0130 Zulu, so a 0-minute lag time. So I've incorporated different lag times of the satellite data into this Unet. So because I have 7 different spectral bands, and in this case I have 3 different lag times for the satellite data, I have 21 channels, or 21 2-dimensional maps going into this Unet. And those are all the predictors, and I'm trying to figure out where is convection going to be half an hour in the future. So the target, or the thing I'm trying to match, is a convection mask. So it's just a binary mask. It's a 0 or 1 at each grid cell, and it's valid at 0 to 100 UTC. So you're seeing that mask in the bottom right-hand panel where the black dots are. So you can ignore the color map for now because those are the predictions coming out of the Unet. So the black dots or the stippling on top are telling you where convection actually occurs 30 minutes into the future. And that convection mask, or the correct answer is the ground truth, is created by applying an echo classification algorithm to the radar data. And that echo classification algorithm is not really mine. It's mostly taken from Cameron Homeyer, who developed the GridRad data set, but I made a few tweaks to it. So it's all explained if anyone is really curious about knowing how this works. It's in this Lagerquist et al. 2020 paper. And then finally, the last portion of this figure that I haven't explained is the color map in the background. So on the in the bottom right-hand panel, this color map is showing the forecast probabilities from the Unet. And you can see that generally there's a good match between higher forecast probabilities and where convection actually occurs. So the higher colors, the purples and reds, which are probabilities of, the purples are 45 to 70%, and then the reds are anything above 70%. Those purples and reds generally correspond to the areas where there's abundant convection, lots of black dots. And here you're seeing a GIF. So this is just a sample at going at 2-hour time steps for 1 day. So you can see the evolution of where convection actually occurs with the black dots, and then the forecast probability field with the color fill in the background. So again, the forecast probabilities are coming from the Unet, and the black dots are showing where convection actually occurs. So in general, there's a pretty good correspondence between the actual convection and the higher forecast probabilities, although obviously it's not perfect. So one thing I really wanted to talk about here, one of the final goals of this last lecture, which Imme sort of alluded to a few minutes ago, is talking about how to really thoroughly evaluate a model. So often when people evaluate their models, whether it be machine learning or otherwise, people will take their entire validation set or their entire testing set and compute a few statistics. So they compute their accuracy, they compute a ROC curve, they compute mean squared error or something like that, and they just average it over the whole validation or testing set. So they get one number or one figure or one graphic that characterizes that entire evaluation set. But that's usually not enough to tell you what's really going on. It's not enough to tell you the strong points and the weak points of a model. So what I really like to do in my work, and something that I always emphasize with people, is when you do your model evaluation, really break it down by time of day, break it down by time of year, by geographic location, by weather regime if you can. So for example, for the tornado prediction stuff that I did in my PhD, I broke down the evaluation by how well the model does on supercells versus how well the model does on quasi-linear convective systems. And it ended up performing much better for supercells and much worse for quasi-linear convective systems. And that was just something I wouldn't have found out if I did the evaluation for the entire testing set at once without breaking it down that way. So here on this slide, you're looking at a performance diagram. So you've seen performance diagrams already pretty abundantly throughout this course. So again, just as a refresher, on the y-axis, you're seeing probability of detection, and the x-axis is success ratio, or 1 minus the false alarm ratio. And each point in the curve corresponds to a probability threshold. And then in the background, the color contours correspond to critical success index, and the dashed lines are frequency bias. So you want to be further as far to the top right of the performance diagram as you can possibly be. You want to have a higher CSI, basically. So here I've broken down performance on the validation data by time of day and time of year. So on the left-hand side, you're seeing time of day, and I know these labels aren't super easy to read, so I probably need to tweak my color scheme. But on top of each one of these curves in the performance diagram is the hour of the day in UTC. So there's at the top left, you're seeing 00, and there's a 01, 02, et cetera, et cetera. But basically what this left-hand panel is showing is that there's not a whole lot of difference in performance as a function of time of day. So the performance seems to be worst around 13 Zulu, 12 to 14 Zulu, and I believe Taiwan time is 8 hours ahead of UTC. So 12 to 14 Zulu is 8 to 10 p.m. Taiwan time. So the performance of this this convection forecasting Unet tends to be worst in the evening, and it tends to be best around 06 to 08 Zulu, which is 2 to 4 p.m. I believe, yeah, 2 to 4 p.m. Taiwan time. So the performance is best in the afternoon and worst in the evening and kind of intermediate at all the other times. But there's not a huge difference according to hour of the day. But then if you split things up by month, which I'm doing on the right-hand side here, and again, I know all these labels aren't super easy to read, but this one curve at the left-hand side, the worst of all the performance diagrams, is for December. So that's the one that I'm circling around with the mouse here. And then the next worst is January, the next worst is March, and then February, and then April. So basically, in the winter half of the year, performance isn't very good, but in the summer half of the year, which corresponds to the darker colors here, performance is much better. And I think that's just because convection tends to be stronger and more organized in the summer versus weaker and less organized in the winter, so it's more difficult to detect. So again, that's something I wouldn't have learned by just averaging things over the entire validation year, which was all of 2017. I also broke down the performance of this convection forecasting Unet by geographic location. So I'm plotting these grids here with different scores. I'm only showing you 2 of the many scores that I plotted. So on the left-hand side, you're seeing Breyer score, and on the right-hand side, you're seeing Breyer's skill score, which is just the improvement of Breyer score over climatology. So for Breyer score, lower values are better, and for Breyer skill score, higher values are better. And I noticed some interesting patterns. A lot of these, you can see lots of rings, especially on the map for Breyer score. The color scheme makes it a little more obvious. You can see all these rings and streaks, and these are just caused by non-uniform radar coverage. There's only 4 radars throughout this grid, and obviously as you get further away from the nearest radar, the coverage at the lower levels, which you really need to detect convection, becomes poorer and poorer. So most of these streaks you're seeing here are artifacts of the radar network, but some of them are really perverse. Some of these streaks are worse than the other streaks, basically. So I found, especially these streaks here, around the west central part of Taiwan. I made these slides a couple days ago when I still didn't know why these streaks exist. I now do know why these streaks exist. They're caused by ground clutter that my echo classification algorithm didn't filter out. So for the most part, it did a really good job of filtering out ground clutter so that it didn't end up being called convection. But there's some really persistent ground clutter in around here that ends up being called convection because it sort of slips past the echo classification algorithm. So I have a whole bunch of so-called convective pixels here, but when the Unet looks at the satellite data, it sees no evidence of convection, so it doesn't forecast convection here. So this is an artifact of just having bad radar data that I need to clean up. And again, that's something I wouldn't have noticed if I just evaluated the whole year of 2017 without looking at how things do as a function of space. And then in the right-hand panel, when you look at the map of Breyer skill score, there's another weird streak that crosses the map basically from east to west, and this is caused by bad satellite data. I wish I had put in an example here to show you because it's probably easier to show you that than explain in words, but there's this persistent line of high brightness temperatures that are just complete nonsense. Any human looking at a map can tell that it's bad data, and it occurs at a whole bunch of different time steps. And that's something that I actually had looked at a bunch of satellite plots before I even started doing my machine learning, but I didn't look at the right time steps, so I never saw the plots that had those weird streaks going through them. So I'm glad I plotted my evaluation this way so I could find those that bad data. Sorry.
That's okay, Brian. Just a quick question. What forecast, data and what model is this using? I forget. I wanted to get coffee.
Oh, the satellite data is from the Himawari 8.
Okay, never mind. There's something with GOES that has streaks because of the grid and then the boundary of the mesh, but so you're not using GOES. Okay.
Okay, no, I'm not. Thank you, though.
Yeah.
So I'll go to the next application here, and this is the last CIRA application that we're going to talk about, and then we'll throw you back to Imme for kind of the wrap up. So this application is radiative transfer, and again, I'll just spend a minute or so motivating this problem. So radiation obviously is a very important component of the global energy budget. The atmosphere warms in areas where you have radiative flux convergence, and it cools in areas where you have radiative flux divergence, and that radiative heating or cooling is really important. And obviously, because it's important as a physical process. It's also important to numerical weather prediction, or NWP. So inside NWP, radiative transfer is not done as part of the dynamical core, so it's included as a parameterization instead. So a radiative transfer model is run independently in each column of the NWP model generally. So we assume that each horizontal location can be treated independently by a radiative transfer model. The most accurate radiative transfer models are line-by-line models, which explicitly simulate absorption by each molecule in each spectral band. So in this figure you're seeing on the right-hand side, you can see absorption lines from methane, water vapor, ozone, carbon dioxide, etc. So even though the line-by-line models are really nice, they're super accurate, they're way too slow to run inside an NWP model. I think the number I've heard is 1 trillion times too slow, so 10 to the power of 12. So even with Moore's law, we're not going to get there anytime soon. So typically, instead of using a line-by-line model, the radiative transfer model used in NWP is a faster but less accurate version, and the rapid radiative transfer model, or the RRTM, is a popular choice. But even the RRTM, the rapid radiative transfer model, it's still too slow to run at each time step inside an NWP model. Generally, the RRTM is run at every 20th time step. So for the intervening 19 time steps, you have to assume that all radiative properties remain the same, and obviously that decreases the accuracy of your overall NWP model. So generally, there's a trade-off here between accuracy and computation for radiative transfer. There's a lot of work that's been done by Vladimir Krasnopolsky and some of his collaborators over the last 2 decades using machine learning to create faster radiative transfer models, so to improve this trade-off between accuracy and computation. So people often think of machine learning as being computationally slow and computationally expensive, but actually compared to running a radiative transfer model, machine learning is much less computationally expensive. The training part is, so I think we've talked about this in earlier lectures, the training part is often computationally expensive, but once you have a model trained and you have the weights frozen and you're just applying it to new data, a machine learning model, even a really complicated Unet, is much less computationally expensive than running the full RRTM. I think the one I've created is about 1,000 times faster than running the full RRTM. So we're continuing this work that's been done with using machine learning to create faster radiative transfer models, but doing it with deep learning. So for the Unet I've created, and I'll get around to the Unet architecture in a couple slides from now, I just want to talk about the predictors and the target variables first. So the predictors include 12 vertical profiles that all come out of the rapid refresh model, or the RAP. There's profiles of temperature, pressure, relative humidity, specific humidity, liquid water content, ice water content, and then we have the downward integrated, so integrated from the top of the atmosphere going down, the downward integrated liquid water path, ice water path, and water vapor path, and then we also have the upward integrated liquid water path, ice water path, and water vapor path, so integrated from the surface going up. And often having both of those profiles integrated downward from the top and integrated upward from the bottom, they provide complementary information. The other predictors are just 2 scalars that also come out of the RAP model. One is solar zenith angle. I mean, I guess that doesn't come out of the RAP model. You can just calculate it for any point on Earth, so it's not really a prediction. And the other scalar is the surface albedo. And then the target variables, currently we're only dealing with shortwave radiation, but eventually we're going to incorporate longwave radiation as well. I'll flip to the next slide. The only thing that changed is the figure on the right-hand side there. So the target variables are a full profile of the shortwave heating rates. That's the orange line you're seeing in the figure here. And then the surface downwelling flux and the top of atmosphere upwelling flux. So even though on the right-hand side you're seeing full profiles of the upwelling flux and downwelling flux, the only fluxes that I'm predicting with my Unet are the surface downwelling flux, so the bottom of all those fluxes, and then the upwelling flux at the top of the atmosphere, because those are the only fluxes that an NWP model needs to know about. So those are the only fluxes it takes out of the radiative transfer parameterization. Other than at the surface and top of atmosphere, the only thing the NWP model cares about is the heating rate. So the training data.
Ryan, I just wanted to say we also want to get to GAN still if we want to, if we can. So it would be great if we could speed up a little.
Okay, I'll speed it up a bit. So to summarize this slide, the training data come from the years 2017, 18 from one set of sites, and then the validation data are from a different year and also from different sites. So the validation data come from different time steps, but also different locations on Earth. So the validation set tests how well the model generalizes in both space and time. Since we're short on time, I'm not going to spend too much time on this Unet architecture because Imme has already shown you what a Unet looks like. The only thing that's weird or fancy or different about my Unet is that most Unets only output an image. So that's what I'm doing here on the top right-hand side. This is one of the outputs or predictans coming out of the Unet. It's Sept, the H means 73 heights by one channel. So this is my profile of shortwave heating rates. So this is one thing that the Unet predicts. And another thing the Unet predicts is those two scalars I just told you about. So the surface downwelling flux and top of atmosphere upwelling flux. And in order to do that, I threw two dense layers on the bottom of my Unet. So it outputs the fluxes from this dense layer, and it also outputs a profile of shortwave heating rates from this not dense layer, this convolutional layer. So again, I wanted to emphasize breaking down model evaluation by time and space and weather regime, etc. And there's some really interesting stuff that I discovered by doing this that I otherwise wouldn't. So this is kind of a teachable moment or a story, I guess. So originally, I was looking at performance on the validation data. So different sites than I used in training, also for a different year, 2019, and the performance didn't look great. So on the left-hand side, you're seeing a profile of the bias for shortwave heating rate. That's in units of kelvins per day. And generally, for this to be useful inside an NWP model to implement as a parameterization, we want to keep the absolute bias less than 0.06 kelvins per day at all heights. And you can see in the lower troposphere, the bias is pushing 0.06 kelvins per day. And then up in around the tropopause, around 15 kilometers above ground, the bias is minus 0.15 kelvins per day. So much more bias than we wanted to see. And also, if you look at the reliability curves, these are color-coded by height. So for the lower heights, which are in the blues and greens, there's an under-prediction problem. The predictions for shortwave heating rate are generally too low. So I didn't like what I was seeing there. But I thought, I wonder how, so I had 13 sites in my validation set, and I thought, I wonder how the performance varies by site. So I decided to plot that. So again, I'm plotting the vertical profile of bias here. This is because it's for 13 different sites, I split it up into two figures because I didn't want to put 13 lines in the same figure. So on the left-hand side, you're looking at some of the sites, and on the right-hand side, you're seeing other sites. And notice the difference on the x-axis. So on the right-hand side, the x-axis goes from minus 0.10 to plus 0.04, whereas on the left-hand side, the x-axis goes all the way down to minus 2.7 or something kelvins per day. So you can see that the bias profiles are looking really good for almost every single site in the validation data, except this weird one, which is Summit Greenland, which is causing all kinds of problems. So I looked at a bunch of individual profiles for Summit Greenland, and I found that the data were wonky. Basically, I had a whole bunch of bad data. I was using this Unet that I'm training, I'm trying to emulate the RRTM, the Rapid Radiative Transfer model. So I'm treating the RRTM answers for shortwave heating rate as the correct answers, but just trying to create a Unet that runs much faster. And when I looked at the heating rates coming out of the RRTM for Summit Greenland, a lot of them were over 100 kelvins per day. Some of them were over 1,000 kelvins per day, and those are just not physical. So this is how I figured out that I had bad data at Summit. Once I took Summit Greenland out of my validation set, this is how the performance looked. So I no longer have bias at any height. There's no absolute bias greater than 0.06 kelvins per day. Actually, nothing is even worse than 0.04 kelvins per day. And if you look at my reliability curves now, they basically all follow that x equals y line. So the model is much more reliable as well when I take that bad data out of the validation set. I also like to break things down by cloud regime. So the green curve here is showing you the performance for clear sky cases that have no cloud. The orange curve is for cases with a single layer cloud, and the purple curve is for cases with multi-layer cloud. And in general, if you look at the training or validation set, clear sky or no cloud cases dominate the training and validation sets. This is by far the most common category, and multi-layer cloud is the least common category. So generally, the machine learning does better for the cases that it's seen a lot of and worse for the cases it hasn't seen a lot of. So there's still problems here for multi-layer cloud that I'm trying to improve, because these biases are a little bit higher than we would like to see, getting down to minus 0.07 kelvins per day, and we don't want an absolute bias greater than 0.06. And finally, Is this, yeah, the last couple figures I'm going to show for radiative transfer, again, breaking things down by cloud regime. So far I've only shown you the evaluation for that profile that I'm predicting, which is the profile of shortwave heating rate, but I'm also predicting the surface downwelling flux and the top of atmosphere upwelling flux, which are those two scalars. So showing the attributes diagrams here broken down by cloud regime. For all three cloud regimes, the predictions of surface downwelling flux on the left are quite reliable. The predictions of top of atmosphere upwelling flux in the middle are quite reliable. But when I look at net flux, which is just surface downwelling minus top of atmosphere upwelling, there's a problem for multi-layer cloud. The predictions of net flux for multi-layer cloud are generally way too high. So this was assigned to me that I had to explicitly. Initially, net flux wasn't actually an output from my Unet. It was just something I was calculating after the fact by taking surface downwelling minus TOA upwelling flux. And this pointed, this told me that I need to explicitly make net flux an output of my Unet so that it can be penalized on the loss function and I can make the Unet do better on net flux. And I see Imme is getting ready to go to the next section. So I'll just maybe 30 seconds here. I also broke things down by time of day and time of year. So you can look at how the performance for net flux varies by time of year, which is the month here, and then time of day, which I've quantified by solar zenith angle. So a zenith angle of 0 degrees means the sun is directly overhead and 90 degrees is on the horizon. And I found that generally as the sun gets lower towards the horizon, the performance for net flux gets worse. And I'll turn it back over to Imme. And how do I stop sharing my screen? There you go.
All right, can you see my screen in full screen mode, I hope? Okay.
Yep.
So we only have a few minutes left, so I will make it really short, but I just wanted to get very, very briefly into GANs, Generative Adversarial Networks. Two acronyms we're going to use, GAN for Generative Adversarial Network and CGAN for Conditional Generative Adversarial Network, which we actually use more often. So very basic idea, again, we only have a few minutes. Very basic idea is you have two neural networks. One is a generator and one is a discriminator. And the generator generates, say, images. And the discriminator is being fed either the images from the generator or real world images. And the job of the discriminator is to figure out whether it got a real or a fake image. And the whole point of including this discriminator is that through backpropagation, the discriminator can then tell the generator how to make its images more realistic. And that's actually an ingenious idea that's only 5-6 years old. And that's really revolutionized a lot of things. So again, the generator is a neural network that generates fake images. The discriminator is a neural network that determines whether any image that it is given is fake or real. And so the two networks really work against each other. The generator always tries to generate fakes that the discriminator can't detect. Kind of like, you know, a criminal making counterfeit money. And the discriminator is a police who's trying to detect the counterfeit money. So it's trying to figure out whether they are fakes or not. And so the two of them are really adversaries, and that's where I think the name comes from, adversarial network. All right, this one you can read on your own. I knew I wouldn't have time to go through that, but basically you log the generator, train the discriminator, then you log the discriminator and train the generator. But the key point is once you have your thing trained, you have this blue thing to use, which is now a generator where if you feed in a random vector, it will generate different samples that look very much like real world images. So once you train it, you just have this blue thing left. And I know it's very weird that you have a random vector here, and you will see that that's actually different in conditional GANs, but just imagine you want to generate houses or whatever, lots of different things. You just feed in a random vector and it will spit out a new sample, right? So you feed in the random vector, out comes a sample of whatever type of image the network was trained to produce, which can be human faces, cats, dogs, fashion. You'd be surprised there being handbags being designed like this, t-shirts, shorts, you know, houses, landscapes. And just to give you an idea how far we've come, this was a recent tweet by Ian Goodfellow, who is the inventor of GANs. In 2014, when they were invented, this is what we could do in terms of generating a face. In 2015, this is what we could do. Still, you know, doesn't quite look like a picture. 2016, 2017, look at 2018. This person doesn't exist. This is a fake. this is something that the generator generated. And so, you can do that for faces, dogs, cats, fashion, art, music. People are using this for compositions. Architecture, landscape. Can we use it for generating climate model output to generate more ensemble members? Can we use it somehow for satellite imagery? So the caution I would say is that the samples that are generated by the GAN when you feed in these random vectors are not representative of the true distribution. The individual samples may be great, but the set of generated samples does not really span the entire space well. So, and that might be fine for a movie that you just get a solution, but not for methodological applications where we really need to know about the actual distribution. So that's one of those things that the methodological community needs to figure out how to address this. And here's a start paper if you want to look into this a little. And again, this is 2020, right? This is all just happening now that we figure out how should we be using GANs. But to give you a little bit more overview, again, the GANs, they're number one, very hard to train. They don't converge easily. They get into cycles, they get into mode collapses, and I won't get into details what that is. But their main function is to generate images. And applications are to generate a large number of samples that are indistinguishable from real ones, and also for in-painting, filling in missing areas of an image, to create something in there that fits that image. Conditional GANs, which I much prefer, you have much better control over, and you will see in a second why. And so I jump into those. They're much better behaved, they're easier to train. They don't generate images, they transform images. So they map an image from one style to another, more like an image-to-image sensation farm. And typical examples, what you might have seen is super resolution, going from low resolution to high resolution images, both in space and in time. And then the other application is image translation, such as our, something like Gremlin, but with higher quality output. Just notice that people are not always careful to distinguish between C-GANs specifically versus GANs. So you might quite often see people talking about GANs and what they really mean is C-GANs. Whenever there's an image or something at the input and not a random vector, it's a C-GAN. Whenever there's a random vector in there, then it's a general GAN. Okay, so just quickly, super resolution, what you can do with C-GANs. So super resolution is an ill-defined problem. If you try to map from a low resolution image to a high resolution image, that is just underdefined, right? The low resolution image doesn't have enough information. And so there are infinitely many solutions. And the question is, how can we fill in that missing information? But we have also additional information. Only certain small scale patterns are actually physically possible. For example, you can only have certain gradients in satellite imagery, maybe, or certain patterns. And the question is, can a neural network learn which small scale patterns are possible by looking at many, 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 many high resolution images, learn which kind of small scale patterns exist, and then finish out the large scale patterns using this small scale patterns. And this is then what a C-GAN looks like. So in this case, let's say you have a high resolution image, a real image, and then you're just downsampling it to create a low resolution image. You feed this into your generator, which now makes a fake high resolution image out of it. Out comes this high resolution image. And now you randomly feed either the high resolution fake plus the low resolution one, or the high resolution real plus the low resolution one into your discriminator. So the discriminator always gets, if you follow this green pathway, it always gets a low resolution image. But in addition to the low resolution image, it gets either the fake or the real image. And it has to figure out whether this is fake or real. Okay, so again, you randomly feed either the fake or the real in high resolution along with the low resolution. What do these neural networks look like? You actually know all of those by now, because the generator is just a neural network for image-to-image translation. So it has inside an encoder, decoder, or a Unet typically. Sometimes it's much more complex, but most of them have just an encoder, decoder, or a Unet in there. The discriminator takes an image and comes up with a label, so it's a classic neural network for classification. So it's the type of neural network that Ryan told you last time about, which is a CNN with fully connected layers at the end. So you plug those kind of things in here, you couple them and train the whole thing. And then what you get at the end, you only, once you have it trained, you only keep this part. which has now been trained to generate high resolution images from low resolution images that really look indistinguishable to the discriminator. Okay. And this one I just replaced what's in here. So instead of going from low resolution to high resolution, you could go from GOES to Mrms. Otherwise, nothing has changed. So just showing you some results. There was a recent paper, again, 2020. You see all of this coming out just now. So this is work by our neighbors here, NOAA and Golden. And they wanted to estimate the typical solar or wind power in the future climates by upsampling GCM estimates. So your GCM, in this case, they use NCAS Community Climate System Model, has a resolution of 100 kilometers, but they wanted to have a resolution of 2 kilometers for their solar and wind power projections. So they used the CGAN to map from 100 kilometers to 2, and in fact, they used 2. They used low resolution to medium resolution, then another one, medium resolution to high resolution. And you can read this part on your own, but I wanted to show you some results here. So the U and the V are the different wind directions. So this is now a wind. And here is the low resolution input. Here is an interpolation of SR, stands for super resolution, and you can see that's not so great. Here's the convolution neural network output, so a typical encoder, decoder, or something of that sort. Here's your CGAN, and notice that they only say GAN. And then there's a ground truth. And so the quick results here to point out is the interpolation is not great, right? The CNN result is a lot better, but it's still fuzzy. And that's because the CNN delivers kind of an average of all the possible solutions. And when you take an average, you always get something fuzzy, right? The CGAN solution looks much, much more realistic, but it's not actually the ground truth, right? And in fact, if you take a pixel by pixel difference, the CNN might be closer to the ground truth than the GAN is. So if you think of that as ensembles, think of the CNN result being the average of an ensemble. So it's a safe bet, the lowest MSE error, but by itself is not physically possible. You could see right away that this is not how small scale features look. The CGAN result, think of that as one member of the ensemble. It's physically possible, but the MSE might actually be worse because it might be far away from the ground truth. And so the caution is, again, if you think, oh, just generate lots of those samples, it doesn't really reside in the real distribution, but it gets you at least something that's by itself physically possible. So this is, I think, my last slide on GANs. Again, this is just a reminder. Imagine you have a low resolution image, which is not shown here, but then you're scaling it up, and the red ones are all kinds of different solutions. So the GAN is just going to pick one of those solutions, this orange thing here, while the CNN is going to pick the average of them all. So no wonder the CNN results are always fuzzy. So this gives you the average kind of, and this just gives you one sample. And if you try it with many different outputs, you're still not going to get the full ensemble over here. So what's better, CNN or CGAN for your application? It really depends on your application, So, and the key point is, again, the CNN is the average of possible solution, but it's not itself physically possible. The CGAN generates one possible solution, but not necessarily the right one. So you have to decide in your application what's better. Before I come to the very last slide where I ask for discussion, I just wanted to show you quickly AI's bumpy road. You may or may not know that we've already seen 2 AI winters where, was inflated hype of what all we can do, and then it turned out it didn't work so well. Then again, hopes were high, didn't work so well. And then what you see here is when deep learning was kicking in. Nevertheless, if you compare the hype to what it actually delivers, we might have another winter, especially we might have one meteorology. But overall, we're probably going to see at least something steady here ever since we got to deep learning. And with that, I come to my last slide here, where I ask, the suggestion and questions. Is there anything specific you need from us to move forward? And I don't know whether we can provide it, but you can at least ask. And with that, I will stop sharing my screen and just feel free to turn on your video or not. But we wanted to hear from you either now in the chat or later by email, what you think would help you. Would it help to have a peer group that meets like once a month and just chats. There wouldn't be us presenting, there would maybe more be people exchanging what experience they have or hearing about something. Any suggestion? Oh, there's a question here. How long will the recordings and sample code stay on the web? Well, the default by GoToMeeting is 1 year, and I'm hoping to extend it beyond the year. Okay, I think some people have to go. So my question, or our question to you, what would help you to move forward? Is there anything we can easily do that would help you? And feel free to send us email.
I'll take, getting back to my point earlier today and wanting to build community here, that keeps something going. I myself am not able to use this information directly yet, but I want to keep my pulse on it, and I think it would be good for other teams maybe have the same idea. So Ryan's idea in the chat of a monthly or bi-weekly meeting, that rings well on my ears, and I would choose probably monthly only because we already have so many meetings now in this world. But even just to hear what people are getting involved with, if anything, that would be useful, if only from the standpoint of keeping a pulse on things. So I support that idea.
Other feedback. I think, yeah, every 2 weeks, I think office hours is one thing, but if you really want to have people to chime in, I think once a month makes more sense because people won't come more often. And you have a better chance of getting a big enough crowd once a month than if you do it every 2 weeks. Any thoughts?
Yeah, I agree with what you just said, and I'm also in a similar boat with John, where I'm not using machine learning right now, and I don't foresee it in the near term, but it would be nice to know that you or someone else is available to ask questions once that, once work does go into that direction. So I don't know, in that sense, the office hour sounds like a really nice tool, but yeah, that's kind of my thought.
Okay. And office hours, how often do you think makes sense?
Yeah, I mean, for I'm not using it in the near term, and I don't. So I it's hard for me to say, but maybe like just for people to know that they could contact you to set up meetings on a as needed basis would probably be the most efficient. But I don't know.
Yep, that makes a lot of sense to me, because I think if we have office hours every 2 weeks, I could imagine not that many people showing up because it doesn't align with people's schedules, what they just need when they need it, right?
Right.
Yeah, I think my motivation with office hours was just to keep a standing resource there, so that people aren't afraid to come with questions. So people know that, I'm actually available, and I'm not just saying that, and then I'm going to ignore your email for weeks after you email for help. But that is a standing resource that I'm offering to anyone here. If you have, if you just want to know more about machine learning in general, if you're struggling with the material, or if you have a project where you're trying to apply machine learning and you don't know where to go next, or you just want a second pair of eyes on something or whatever, that's something I've done for a lot of people, and I'm always happy to do it.
Yeah, Ryan actually enjoys doing that. So he can't solve the problems for you, but he loves to give feedback.
Right, Ryan, do you know what you are getting yourself into? Well,
Perhaps not.
From my perspective, I think I might have suggest some questions, but I have not done enough legwork yet to be there. But thank you for the generous offer, both of you. I'm sure we will use it. Actually, I'm trying to develop an event viewer for NOAA Ocean Division, and this is where some of the things will come handy, I'm pretty sure. Okay.
Any other
great.
comments?
I'm glad to hear that.
Thank you.
If we were to have a meeting like once a month, it would just basically be a meeting point where people can ask questions or tell us what they've been up to, that kind of thing. But it wouldn't be us teaching you things, That would be probably beyond our bandwidth to have a lecture every month, really, that fits for everybody too, topic-wise. So more like a chatting place where people can gather and talk about machine learning things that they've heard or that they want to know about or whatever. Would people be interested in something like that once a month?
Yes,
Or
sure,
everybody
definitely, certainly, no doubt about that one. But how much individually people can contribute will depend where we are
Oh,
at.
sure. There's no pressure on anybody. Anybody can just sit and listen. You know, it's basically just an hour, maybe an hour once a month where we just say we're meeting and there's not even a gender. It's just, we just chat. It's more like meeting in a cafe, you know, and we just chat.
For that, apropos that idea, my thought is to schedule that because people schedule, we're in different time zones. And perhaps an hour, sometimes it's too long and sometimes it's way too short. I would maybe consider a 90-minute window. So people in different times, some people are like, oh, I'm about to have lunch, et cetera, and with maybe the rule being if nobody is there for 15 minutes or more, it's just shut down. And that way people could jump in and go, but it allows for a slightly wider range. Of course, that's more of your time taken up sitting waiting. Is somebody going to show up? But you can just be, you know, like the old college rule, the professor's not here for 15 minutes, class is canceled. And it's just the opposite. No students have shown up today, bye.
Or just Ryan and I both showing up, and otherwise we just talk. Ryan and I, we always have stuff to talk about. So
yeah, exactly. Thanks
Sounds
for that
good.
input, John. Yeah, I really like that idea too.
Okay. If you think of any other things, send us email, send us suggestions, either to Ryan or to me, and we'll think about what we can do. Other than that, I thank everybody. I will stop the recording now. Are there any questions right now?